Hello, welcome back. Let's continue with our calculation. Alright, before we continue, after careful review of our previous calculations in our last session, I discovered I made an error or two errors, but don't be alarmed, the errors are very minor. Yes, so this is one of the errors. This is not a multiplication sign, rather an addition sign, but the evaluation is okay. It was just the sign. And the last error, yes, so here is the last error. Instead of 10,650, we are supposed to have 10,670. Why? Because this value is 10.67. Multiplied by 1,000, you will be having 10,670, not 10,650. So let's take this step all over again up to the last point, even though the difference will not be much. So it is due to this minor errors that some corporate entities are developing toolkits that will aid you in calculating all this seamlessly. All you need to do is just to input your data and they will run the calculation for you. I know of Syntajon. They've developed a toolkit that will help you in this type of calculations. Though I have not used the toolkits, but I commend the idea. So now bringing out our calculator. $10,670 multiply by 0.000015, we'll be having 0.16. so if we round it up, you will see we are having the same value. So I think everything is okay downwards, so let's just leave it at that. But it's good that we corrected this so that when you come to revisit this calculation page, you will not be confused. So moving on, now remember we are calculating the friction in our rubber hose. So let's see. Alright, this 10,670 is okay. I thought I made the same mistake. So .000, there's something missing here. Let's recalculate. 0.02, which is our pipe diameter in meters, raised to the power of 4.8753. So 9 zeros and 53. 1 2 3 4 5 6 7 8 9, then 5 3. Okay, $10,670 multiplied by 0.00000077, 0.0082, 0.0082 divide by open bracket 8,818 multiplied by 0.0000000053. We are having 0.000047. Let's round this to 47. 0.000047, right? Is it 5 zeros? 1, 2, 3, 4, 5. Yes, 47. Okay. Which implies that our H3 will be equals to, let's evaluate this, 0.0082 divide by 0.000047. We'll be having 174. Yes, 174. Okay, let's yes, 170. Okay, let's say 175. 174.4 meters. Say 175 meters. So this is the loss we are going to have in 1,000 length of pipe. So now therefore for 36, remember our hose is running 36 in length. For 36 meter of run, our H3 will be equals to 175 multiplied by 36 divided by 1000, which is equals to what? Six divided by 1000, which is equals to 6.3 meters. So that's our H3. Now our H4 is suction head plus delivery head. Remember our delivery head we said is the height of our building. So the height of our building is 7 meters, while the suction head is 2 meters. So this suction head is the pressure encountered when the pump is exerting an extra energy to siphon the water from the source. You know, the pump has to create a vacuum in order to siphon water from the source. For instance, like people that use what do I say, jerrycan to fuel their car, maybe when they run out of fuel. When you are using jerrycan and a hose, you know, you have to blow air into the jerrycan. So blowing that air now creates a vacuum that will siphon the fuel through the hose and deliver to your fuel tank. So it's the same principle the pump is following. So let's continue with that. Now we have 7 plus 2, which is 9. Let's say 10 meters. I'm only adding this for factor of safety, but we can leave it as 9. There will not be, it won't be bad to do that. So now nozzle tip discharge. Remember the required pressure, the minimum required pressure is 200 kilopascal. So now in order to attain this, of course there are forces the pump needs to consider, to take care of. So let's convert this now to meters. Convert the pressure delivery head using the below formula. So this is the below formula. The head we are looking for now in meters is equal to the pressure over density of water times acceleration due to gravity. And remember, our required pressure, as we said, is 200 kilopascal. The density of water is 1000 kilogram per meter cube. I'm sure you recall all this. Acceleration due to gravity is g, which is 9.81 meter per second squared, right? So now head equals to 200, that is using our formula, 200,000 pascal. We are converting this kilo now to pascal. That is why it's 200,000, not 200 anymore. Divide by 1000, which is the density of water, times acceleration due to gravity. So now after doing this, what we are going to get is, we can recalculate, but it's still the same value we will arrive at. 200 divided by 9.81, so 20.39. so say 20, no, let's say 21. So that is that for our H5 I mean. Our H6 is pump loss, which is 2 meters. So now bringing all these values, all these heads we've calculated into the general formula to get the total head. Now let's do that. What is our H1? Remember, we got 1.4. Am I correct? Yes, 1.4. Sorry. Okay, yeah. So our H2 what is our H2? Okay, our H2 is the number of fittings, which is 5 meter. Remember, each fitting is 0.5 meters, right? And we said we are assuming 10 number of fittings, so 5 meter. Okay, so what is our H3? Frictionless due in our rubber hose, which we got to be 6.3. H4, which is our suction head plus delivery head, which is 10 meter. And our H5 is 21. Okay, while our pump close is 2 meters, which is H6, right, plus 10% factor of safety. So let's calculate all this. Let's sum them up all. 1.4 plus 5 plus 6.3 plus 10 plus 21 plus 2, 45.7. So 45.7 meters. Now remember, we are adding 10% factor of safety. .57. Are we correct? Let's do this. 10 divided by 100, 0.1, yes, times 45.7, 4.57. So summing this together, 4.57 plus 45.7, 50.27. So let's say 50.3 meters. All right, so now we have our total head of which is H, right? 50.3 meters. So now to calculate for the pump set capacity, it is mass times acceleration due to gravity times total head all over pump efficiency of 65%. For this efficiency, I think we can step it up to 80%. Why? Because with the advancement in technology, I believe it is possible to have an 80% efficiency for pumps nowadays. So let's step this up to 80% efficiency. So for this mass, recall that 1 kg of water is equals to 1 liter of water, and remember we said our rate of flow is 2.5 liter per second, so 2.5 kg. So Now 2.5 kg will replace this 2.5 liter in this formula. So pump in watt now, whatever we get will be in watt. So 2.5 times 9.81 times our total head, which is 50.3, times 100 divided by 80. Remember, we stepped up our efficiency to 80. So let's do this calculation and see. 2.5 times 9.81 times 50.3 times 100. Yes, so we'll be having 123,360. Now divide by 80. We'll be having 1,542 watts. $1,542 watts. Do we need to round up? No, I think since this is 00, we can just leave it as 1,542 watts. All right, so now to convert to kilowatts, we'll divide this by 1,000, right? 1,542 divided by 1,000, we'll be having 1.542 kilowatts. So you can easily say 1.5 kilowatts. Now recall that 1 horsepower is equivalent to 0.746 kilowatts. So now we want to get this capacity in horsepower. So now 1.5 kilowatt divided by 0.746. Divided by 0.746, and we will be having 2.0. Watt. Let's see, we can leave it at 2.0 horsepower. So add up two numbers of pumps of 2 horsepower. So you can see our pumps are not that big in capacity. Why? Because we have only 2 floors. So since the floor is not too high, 2 horsepower will be able to give us the required pressure to fight any fire outbreak in this building. So, and the pumps, one will be electric, meaning it will be operated with electricity, while the other will be a diesel pump in case if there is power outage and there is fire. You won't say you don't need your hose reel to work. Why? Because you don't have light. So diesel pump will now take over to power the pumps, so that at all time you have a backup solution. When there is power outage, of course you have your diesel pump to take over. So now our head is 50.3. So that's that for our pump sizing. And this now is these two pumps now can sometimes be complemented with a third pump called a jockey pump. A jockey pump is a minor pump compared to these two pumps. All it does is just to make sure that there is the pipes are always charged with water. There are loses even when the pipe is completely insulated. Water will definitely find little gaps to escape, so your pipe will be draining gradually. So what this jockey pump does is to detect this drain, to detect that your pipe is losing water, and then start to make sure that the pipes are always charged with water to the brim. So that is the work of the jockey pump. It's a booster pump. It always ensures that your pipe is charged with water to compensate for losses, minor losses. So that's that. We can go back to our design now and effect this two fire pumps. Yes, 2 horsepower, one running, one standby. Okay. While for this, all right, I believe there is no much to be done. We've already, so for this fire hose reel, which is inserted in a box, it can be located in the wall. It can be hidden in the wall, where the box will flush with this wall, or it can be left outside the way we did it initially. That is this way. So but if your wall can contain this box with the fire hose reel, it will be a more beautiful layout, and there will be no obstruction, more especially for narrow passage. So this fire hose reel will not be obstructing the passage. Why? Because it is flush in the wall. So that's that. If you wish, you can hide it in the wall, or you can leave it out depending on the passage. So for this, remember our diameter is 20. That's what we use for our calculation. So the diameter of the hose itself is 20 millimeter. So let's tag our suction pipe as well. So remember, since we are having 50 mm diameter discharge pipe, our suction pipe should be 70. It should be all 75. Let's make it 75. It should be bigger than the discharge pipe. Why? So that the pump will always be charged with water in order to continue discharging to our hose reels to prevent cavitation and impeller damage. Suction pipe. Sorry, you said 75, right? Yes. Alright, so in our next session we are going to bring in our tank details to demonstrate how the connection is going to be. See you in the next session.